So, in all of this testing that we have done, right, we are looking at a voltage, right. So, it is maybe we can say it is a voltage test, meaning if a node is stuck at 0, what we really mean is its voltage is close to 0. Okay. Remember, in a digital logic, logic 0 really means some low voltage. Okay. If this is 0 and this is VDD, we are willing to consider all of this as logic 0, and we are willing to consider all of these as logic 1. Okay. So, we measure the voltage at the output and then see whether it corresponds to a logic 0 or a logic 1. Okay. So, in a way we are measuring the voltages. In CMOS circuits, there is another method which is called as current testing. So, that is what we will discuss now. Let us look at what a CMOS circuit looks like, right. So, let us draw a CMOS NAND gate or something like that. So, this is your CMOS NAND gate. So, remember that CMOS is inherently low power. What that means is, imagine that I apply a 0, 0 or something like that. So, these are NMOS transistors. So, when the gate voltages are 0, they will be off. So, these guys are off, and the PMOS transistors will turn on, right. Remember that there is a capacitance at the output. There will always be a capacitance. It will be possibly the diffusion capacitance of the PMOS transistors. There could be a metal connection here, and there may be a metal oxide semiconductor, that capacitance. So, there will be some output capacitance whether we want it or not. So, when A and B are 0, these transistors will turn on and cause this output to go from 0 to 1 by charging the capacitance. And when the capacitance gets charged to almost VDD, then you can see that the drop across the PMOS transistor will become close to 0, right. This also is at VDD, this also is at VDD, and that will cause both these transistors to turn off. So, in other words, there is no path from VDD to ground. Okay. So, no path from VDD to ground, which can allow current to flow. Okay. Compare this to a NMOS gate. Okay. In an NMOS transistor, this is how it is built. So all are NMOS transistors. So this is like a, it's constantly conducting. Okay, because the gate is connected to VDD. So by chance, if you apply a 1 here, this guy will turn on, right? And there is a conduction path. Okay, this is like a resistance, and it will lead to significant amount of current flowing. Right. So that is the problem with NMOS. So too much power. The same is true in this is an NMOS gate. The same is true for PMOS as well. PMOS suffers from the same problem, which is the reason why NMOS and PMOS are not used today. Okay, CMOS dominates because in CMOS, between the P part and the N part, there will be never a path from VDD to ground. There will be no constant conduction. That makes it inherently low power. A small current will flow, however, that is called as a leakage current. See, even when we have applied 0 volt to A and B, the voltage may not be exactly 0. Okay, it may be slightly anywhere in this region. So there will be some weak inversion in these transistors, and a current will flow. Okay, you can think of them as very big resistors. Okay, they are big resistors because they are really off. The transistors are off, but there is something called as a sub-threshold conduction, sub-threshold leakage. So a small current will definitely flow. So if I applied 0 0, both of these are on, and these are like high resistors, and there is a circuit here. A small current will flow. The amount of current is sort of, if you look at only one gate, it is not a big deal, right? It's very small. But remember that now we have a lot of transistors. See, we have billions of transistors now. So there is a big chip with lot of transistors. The CMOS circuit, when does it really dissipate power? It only dissipates power when the output changes. So imagine that I have applied a 1, okay, that causes this guy to conduct, and any capacitance, any voltage across the capacitance, okay, that will get discharged. The charges on the capacitance will get discharged, and the output will go to 0. Now, if this were to change from 1 to 0, this guy will stop conducting, This way this guy will conduct and charge the capacitance. So, the output will go from 0 to 1. So, during that period a current will be drawn, a charging current will be drawn. So, charging current when output goes from 0 to 1. In the same way, if the output were to go back to, let us say 1, if the input were to go back to 1, now again this discharging will take place. Okay. So, a discharge current will flow. So, this charging and discharging will result in some energy dissipation or power dissipation. So, if VDD is the voltage of the power, if this is the power supply voltage and C is the capacitance here, then the energy dissipated in charging this capacitance or discharging this capacitance is approximately this value. Half C VDD square. And imagine that we have a clock pulse here. The clock frequency is, let us say, this, and its period is T, and its frequency is F. Now, the input to this NOT gate may change occasionally. Okay, let us say some small percentage of the let us say there are so many clocks, and some small percentage of these clocks, the output is changing from, input is changing from 0 to 1 or 1 to 0. The input changes, input activity factor is, let us say, some small percentage, let us say k, which is much less than 1. Okay. So, for whenever that activity occurs, the amount of energy will be half C VDD square. And we can multiply it by the total number of clocks, right, number of clocks. So, k times number of clocks is the number of times when the NOT gate switches, right. So, if you want to calculate the power, power is energy by time. So, we can say k times half times C VDD square times n clocks. So, n clocks multiplied by time or the period. So, this can be simplified as k times half times C VDD square times f, where f is the frequency. So, 1 over T is frequency. So, this is the active power. The active power only gets dissipated when there is activity in the circuit. That means nodes are changing from 0 to 1 or 1 to 0. And we can multiply this by the number of gates. Okay, actual power will be total power will be in n gates multiplied by this k times half C VDD square f. Unfortunately, this is becoming very large. Okay. F is also increasing very much, and VDD may be coming down little bit, right? Maybe C also is coming down because we are scaling all the transistors, etc. But this is very steeply going up, very steeply. Both frequency and the number of gates are both increasing, and as a result, the active power is increasing. Right. So people design the circuits in such a way that at any point of time, this K is very small. That is, the number of gates that switch is very small. That is how it is done. What about the remaining guys? See, if let us say small percentage of let us say some activity is happening here, the rest of the guys are all quiet. There is no activity. The nodes are they remain charged at either 0 or 1. But unfortunately, they will all dissipate this leakage power. So active power will be dissipated here, but all the other places they will dissipate leakage power. Sub-threshold leakage, for example. Right? Then there are other sources of leakage like gate leakage. Okay, PN junction leakage. So there are other sources of leakage. So what if you had a CMOS circuit and if you power it up, if the supply voltage is VDD, and suppose we measure the current through the VDD, which is referred to as IDD. So IDD is the supply current, or the current drawn from the power supply. So when the activity is happening, that is when the some nodes are switching, right? So if we cause some inputs to go from 0 to 1, etc., some activity will happen. Okay. So if we cause some inputs to change here, some nodes will switch, and as a result the current will go up. But when all the activities have completed in CMOS, no node will continuously remain conducting, right? That's what we mentioned, right? So there is no conducting path. Okay, there is no path from VDD to ground. So ultimately, when all activities complete, the current will come back to a very low value. Okay, so it is practically zero, but it is still there. There is some leakage current. So this is the active current. This depends on how many activities are happening, right? If lot of gates are switching, this it may have a large value, otherwise it may have a small value. This is difficult to predict. But when all becomes quiet, then the current will come down to a small value, which is mostly due to leakage. So what we could do is measure that current, measure the IDD, we say IDDQ. Q means quiescent, right? When all the activities have completed and the circuit has become quiet, then we can measure the current. It should be very small in a CMOS circuit, which is the because mainly due to leakage. So if this is a small value, then we can conclude that it is a good circuit. But if there is some if there is a fault like this, right? Let us say this guy is at fault. I'm sorry, this guy is at fault. Let us say it is permanently stuck at 1. Okay, it's always closed. Now, when I make this 1, this will conduct and so will this. Is already conducting. Okay, and as a result, it will leak. Okay, it will produce a continuous path. Okay, maybe it's easier to appreciate this in an inverter. So let us take an inverter here. Okay, imagine that this guy is permanently on. Then what will happen is when I apply a 0 here, there will be a conducting path. Okay. And both transistors will continue to conduct forever. Okay. And as a result, a fairly large amount of current will flow. Okay. And that current will be definitely higher than this current. So if you look at the currents, let us say this is our leakage current or whatever. And this may be the active, during activity, this is the current. Okay. And when there is no activity, let us say the current becomes somewhere here because of the fault. So take this example. If this is faulty, that is always on, and we apply a 0, then because it is on and this CMOS also turns on, it will continuously leak, it will continuously drop up. So the IDDQ value will be higher, so it will jump somewhere here. It will be limited by the resistance of this. See, they will have some resistance, right? Even the permanently on transistor will present some resistance. Similarly, the PMOS transistor, when it is on, it will present some resistance. So the current that will flow depends on that resistance. So this is the estimated value. It should be a small leakage current that flows when there is no fault, but with fault, it will jump like this. So because of this, we can detect that there is a fault. Okay. So the idea is apply a test vector to the CMOS circuit, wait for all the activities to get completed, and then measure the current through the supply. We expect it to be a small value, but if you are observing a large value, you can conclude that there is something wrong. It could be a bridge fault, it could be a it's difficult to say what is wrong, but definitely something is wrong. So we can use that also to reject bad chips. But you must appreciate that we are making millions of these devices. Okay, so let us take this an inverter, right? Imagine that we have made lot of inverters. Each one of them will be different. Okay, their transistors will be different. They will have different W value, width, length, the thickness of the oxide. Everything will vary. So as a result, the amount of leakage current will also vary. So there is some variation, and if there is a fault, that faulty current will also be subjected to some variation. Okay, we want the separation to be as high as possible. So these are the values that this is a current. Okay, so if I plot, let us say, the probability of the current being this value, so it will have something like this, meaning it's very likely that the current is in this range, and as we go on either side, the current the probability will come down. It's like a normal curve. Similarly, when the fault exists, the probability of the current being some value also will have that kind of a distribution, right? It's very likely to be this value, right? And then it may roll off on both sides. If these are well separated, then IDDQ test will work, right? We can measure the current may vary, okay, but there is a good separation. Okay, another way to understand this is something like this, right? See, when people want to check if a child, let us say, has a fever or something like that, they touch the forehead to see whether the child is running a temperature or something like that, right? That's a very crude way to test, or maybe even we can make with a thermometer we can measure, right? See, 99, 100, 101, 102, 103. See, these are definitely considered problems. See, a child which is running a temperature of 103, 104 definitely has a problem. Okay, whereas 98, these are all normal. Now, this normal is not, it's not that for everybody it is the same thing. Okay, there is some variation. For some people, they have 98 as their normal temperature. Some may have 99. Some may even have 100. Right. So imagine that somebody's normal temperature itself is 100. So if that person is measuring 102, we don't know how to conclude whether it is conclusive enough to say that that person is sick. In the same way, this IDDQ testing, right? Slowly, what is happening is the number of gates is increasing, right? As a result, the leakage current is increasing. Okay, so leakage current is coming in the other direction. See, the leakage is increasing. Okay, and this may be our faulty current. So leakage can be anywhere from here to here, and faulty current can be anywhere from here to here. So you see, it's difficult to say whether there is a fault in the circuit or not. by just measuring the current. This technique was very popular in the, I would say, before 90s. Okay. So, IDDQ testing was a very good way of checking whether a fault exists in the circuit. But with the increase in leakage, with our inability to distinguish good from the bad based on current, right? IDDQ testing is not as effective as it used to be. Okay. So, IDDQ testing is still practiced. They make a few measurements just to get some confidence that all is well. Okay. So, they may make some 10 measurements or something like that. Okay. Because you will appreciate that making these current measurements also is not easy. On the tester, you will need a way to make that measurement in a good way. I mean, in a error free way. Okay. So, there was a time when even sensors, current sensors were inserted into the circuit to make those measurements automatic, right. So, there were built in current sensors, okay, built in current sensors, they were added to the circuit so that the circuit can test itself. If the current value is high, something like this, then the circuit itself could declare that there is something wrong. Is that clear? Okay. So, IDDQ testing is only meant for CMOS circuits, others you cannot do, because CMOS is an inherently low power. That is the reason why IDDQ testing works for CMOS. Okay. But it is becoming less effective, less effective due to leakage currents. So, leakage currents are increasing, and it is difficult to tell a faulty chip from a good chip by only looking at the current. Okay. So, this is also an important, so people do make some measurements. Okay. So, some IDDQ testing is still practiced, okay. But as you can see, it is becoming less and less effective.